Hello everybody. We will revise coordination compounds today. So coordination compounds is a topic of inorganic chemistry. It's extremely important. In order to solve questions related to coordination compounds, one must be thorough with the concept of electronic configuration. One must know Aufbau principle. One must know Hund's rule, right? And also you must remember the atomic numbers of elements from 1 to 30. So be very thorough with the atomic numbers of all these elements. Especially when we talk about the 3D series, that means we are talking about elements from z equal to 21 till z equal to 30. So these 10 elements are of extreme importance in coordination chemistry. So you must remember the atomic numbers of those elements. Right? That means I will do a quick recap of the atomic numbers of the elements of 3D series. So it's scandium, whose atomic number is 21. Right? Then we have titanium. Then we have vanadium. Then chromium. Then manganese. Then iron. Then cobalt. Then nickel. Then copper. And then zinc. So this is the 3D series from scandium till zinc. Right? So this is very important. And also you should remember the concept of hybridization, which we have discussed in chemical bonding. In chemical bonding, hybridization is taught, and that same concept of hybridization is going to be used in this chapter as well. Another important concept which will be used again and again in this chapter is oxidation state. So when we are finding out oxidation state of the central metal atom in a coordination complex, we must remember the basic rules of oxidation numbers, right? So always remember that if you have a fluorine atom or chlorine or bromine or iodine in this chapter, it means any halogen atom is connected to a central metal atom, then the oxidation state of the halogen is always -1. Okay? And also if you have water as a ligand, H2O as a ligand, then the entire H2O is neutral. Neutral means I have to assign 0 on top of the entire water molecule. Similarly, if I have carbon monoxide is what? CO. So here also this is entirely neutral, which means I have to assign a charge equal to 0 on top of the entire CO molecule. So remember, H2O, CO, NH3. All these are neutral molecules. These can act as common ligands in coordination complexes, but we have to assign 0 as the charge on each of these. Also, if you have C2H4 as a ligand, again this is neutral, so again you have to assign a charge of 0 on top of C2H4, right? So these are very common neutral ligands that we come across in questions. So for halogens, oxidation state is -1. Always remember that. Another important thing is when we have CN, the entire CN has a charge of -1. So this is an anionic ligand. Anionic ligand means we have a negative charge on top of the entire species. So this is called cyanide ion. CN -1 is an anionic ligand. So you must remember that the charge on CN is -1. Okay, likewise SO4, if you come across SO4, it is sulfate 2-, so charge on sulfate is 2-. You have to remember this, right? And what else? So Cn-, SO4 2- are very common anionic ligands. You will see them again and again, and obviously halogen atoms. So halides are the ligands. Okay, so you have to remember this. And if you come across this means it's -1. NO2 has a charge of -1. NO2 has a charge of -1. Also, NO3 is an anionic ligand. It has a charge of -1. So you must remember these things. Then only we can start questions of this topic. Okay. Let's start with the questions. So the first question is this. Which of the following does not have a metal carbon bond? Does not. Remember, in organic chemistry, we discussed Grignard reagent, right? This is called Grignard reagent. R means carbon is there definitely in this portion, and this bond is between carbon and magnesium. Magnesium is a metal. So I will say this bond is between carbon and metal. Any species which has a bond between carbon and metal is called organometallic compound. So Grignard reagent is an organometallic compound, right? Now in this question we have been asked to identify the species where there is no bond between metal and carbon atom. So it is option B. You can look at this, right? It's aluminium ethoxide. So here what is happening? With aluminium there is no carbon. It's oxygen which is connected, right? So O, and then you have ET. ET is C2H5. So which means this bond is between the metal and oxygen, not between metal and carbon. Hence B is the correct answer. This is Grignard reagent. Here also if you see it's C2H4, C2H4 is acting as a ligand, and anything which acts as a ligand will definitely coordinate with the central metal. So with platinum you will have a bond here with carbon. Hence this cannot be the answer. Even here carbon is bonded to this one, nickel, right? Nickel is a metal. So between nickel and carbon you have a bond, coordinate bond. So A also cannot be the answer. Hence B is the correct answer. There is no bond between aluminium and carbon in B. This is called aluminium ethoxide. Also written in this way. Al OET thrice, aluminium ethoxide. Let's move to the next question. An aqueous solution of CoCl2 on addition of excess of concentrated HCl turns blue due to the formation of. Okay. So you have to remember this concept. This is blue in color. When is this formed? This is formed when CoCl2 is added to excess of concentrated HCl. Right. What is the oxidation state of cobalt in this? You must remember the oxidation state. I mean, you must be able to find out. Don't remember, don't memorize the oxidation states. I've told you that any halogen atom will have a charge of -1. So this is -1 written on top of Cl. Let the oxidation state of cobalt be X. So X multiplied by 1 plus -1 into 4 is equal to -2, and hence the value of X is +2. So the oxidation state of cobalt is +2 in this. So you have to remember that this is blue in color. Let's move to the next question. The order for the wavelengths of absorption in the visible region is, alright. Now see, we know that the energy absorbed, going back to atomic structure is what? This hc by lambda, where h is Planck's constant, c is the speed of electromagnetic radiation, lambda is the wavelength of the radiation. Now we know that if this is high, energy absorbed will be low because lambda is in the denominator, right? Now this is in increasing order. If you look at the options, the wavelengths are in increasing order. If wavelength is in increasing order, that means the one which is present on this right hand side will absorb the maximum wavelength, right? It is in increasing order of wavelengths, correct? So the species which is written on the extreme right will absorb the maximum wavelength. If wavelength is maximum, energy absorbed will be minimum. If wavelength is maximum, energy absorbed will be minimum. Alright. So we know, going back to the crystal field theory and the spectrochemical series. So if we check the series, we will realize that some ligands are called strong field ligands, some ligands are called weak field ligands. So the spectrochemical series tells us which ligand is a stronger ligand as compared to another. Now, energy absorbed will be more if the ligand is a strong filled ligand, right? So if the energy absorbed is more for a strong filled ligand, out of these ligands NO2 minus NH3 and H2O, we know that H2O is a weak filled ligand, right? H2O is a weak filled ligand. H2 is a weak filled ligand. Since H2 is a weak filled ligand, the energy absorbed will be low here. So the maximum wavelength will correspond to the complex where water is used as a ligand, and hence A is the only option. There is no other option where you have this complex written at the end. So A is the correct answer. Right? Let's move to the next question. The IUPAC name of the coordination compound. Okay, this is very common type of question. Potassium always shows oxidation state of +1, alright. Which means this entire thing will have a negative charge of 3 minus. I mean, -3 will be the charge on this complex. Right. We have discussed today in the beginning that Cn entire thing carries a charge of -1. So let X be the oxidation state of Fe here, which means X plus -1 into 6. Right? We will get the value of X. X is oxidation state of Fe. So it's +3. Hence the correct name will be potassium hexacyano or hexacyanidO ferrate 3. Within brackets we'll write 3 because the oxidation state of the central metal atom is 3. Hence B is the correct answer. Potassium hexacyano ferrate 3. This is wrong because here the oxidation state of Fe has been mentioned to be +2. Whereas we have clearly understood why the oxidation state of Fe is +3 here. So B is the correct answer. Next one. Which of the following complexes would exhibit the lowest value of paramagnetic behavior? Paramagnetism means number of unpaired electrons should be present. If the paramagnetic behavior is very high, that means the number of unpaired electrons is more. But they have asked us to identify the complex where paramagnetic behavior is the lowest. That means the number of unpaired electrons should be the least. Okay. So, what is the correct answer? Oxidation state of Cr is +3 here, oxidation state of Mn is +3 here, because everywhere you have cyanide as a ligand, right? So every central metal atom will have a value of +3 for the oxidation state because the charge is -3 for all and the ligand is same for all, and also the coordination number is same for all, which means the oxidation state of the central metal atom is going to be +3 for all. Alright. Also, Cn- is a strong field ligand. Okay. Now, electronic configurations if I write, then for chromium, I'm just writing the valence shell electronic configuration for the central metal ion. It's 4s1 3d5 for chromium atom, but +3 indicates I have to remove 3 electrons. So I'll remove 1 electron from here and 2 electrons from here. So 5 minus 2 is 3, so it is 3d3. Again, for manganese, it is this. I have to remove 3 electrons of 2 from here and 1 from here. Alright, Fe +3. It's 4s2 3d6 for the neutral Fe atom. So I have to remove 2 electrons from here and 1 from here. So it will be 3d5. Talking about only the central metal ions, right? And for cobalt, it is the atomic number of cobalt is 27. 4s2 3d7. So after removing 3 electrons from cobalt, I'll get CO3 plus, which means these are the valence shell electronic configurations of the central metal ions. Now, following Hund's rule for the d subshell, for the last one, if you see, okay, and one more thing, okay, before going ahead. Cn- is a strong field ligand, so we have to use that concept, that is crystal field theory. Now, these are all octahedral complexes because the coordination number is 6 for each, which means I have to write T2G and Eg, right? So T2G and Eg. So this is Eg and this is T2G. Pairing will happen because the ligand is a strong field ligand. So if pairing takes place, what will happen then? For 3d6, if I have to write 1, 3. And then 4, 5, 6. Look at this. Right. Which means due to the pairing, there is no unpaired electron left. So D is the correct answer. There is no unpaired electron. That means this is not paramagnetic, this is diamagnetic. Right? We can't put an electron here because Cn- is a strong field ligand, and because of the presence of strong field ligand, pairing will take place here itself. So there is no unpaired electron, so no paramagnetic behavior found. Okay, next one. The value of the spin-only magnetic moment for the complex, okay, for one of the configurations is 2.84 bm. Bm is Bohr magneton. So which one is it? All right. Now again, this depends on the number of unpaired electrons. The formula is what? Root of n into n plus 2 Bohr magneton. N is the number of unpaired electrons. Now this value has been given as 2.84. 2.84. So what should be the value of n? So if n is 2, right, then 2 into 4 is 8. Root 8 is 2 root 2. Root 2 is 1.414. 2.8. So it is close enough, which means the number of unpaired electrons is 2. The number of unpaired electrons is 2. So we have to choose the option where the number of unpaired electrons is 2. Also, we have been told whether the whether the ligand is strong field ligand or weak field ligand. Alright, so let's see now. Where do we see 2 unpaired electrons? Now, if we check the first option, that is D4, right, D4. So D4 in strong field ligand. Since it's a strong field ligand, I'll have to start pairing. So D4. And then I have Eg here. This is T2G. This is Eg. Clearly we can see there are 2 unpaired electrons. Hence A is the correct answer. Right? If we check option B, then I have to put 1 here and here 3. T2G Eg. This is for the second option. So if we check the number of unpaired electrons here, we have 4 unpaired electrons, whereas we need 2 unpaired electrons. Hence the correct option is A. Right? Alright. So A is the correct answer for this. Next one. A square planar complex is formed by hybridization of which atomic orbitals? Whenever it is square planar complex, straight away without thinking we know we have to use dsp2 as the hybridization. dsp2 is the hybridization for square planar complex. And B is the correct answer. We have learned this in chemical bonding as well, that whenever dsp2 is involved, then we have S, we have px, we have py, and we have dx square minus y square. Dx square minus y square means the lobes are along x and y axis. Right? So B is the correct answer. dsp2 is the hybridization of the central metal whenever we come across a square planar complex. Next question. The most stable complex among the following is. Now, most stable. Remember, if we have chelation, then stability increases. Chelation increases stability. So the most stable complex will be D, because EDTA itself can form rings, that is chelation is very good here, and hence we will say D is the correct answer. In no other option do we have EDTA. Remember, EDTA can form multiple rings, right? So chelation is very good. Chelation means After coordinate bonds are formed with the central metal, rings are obtained. So more the number of rings, more is the chelation, and more is the chelation, more the stability. EDTA is ethylene diamine tetraacetate. EDTA 4 minus. This is the ligand. It's an anionic ligand. Full form is this. Which means the oxidation state of nickel here is +2. Then only you will get K2NiEDT as the formula, right? This entire thing has a charge of -4. So +2 minus 4 is -2, and then K has an oxidation state of +1. Hence correct option is D. Next one. Which is incorrect? Now this is related to biology. You see cyanocobalamin, you see vitamin B12, you see hemoglobin. So this is strictly biology. This is incorrect. C is incorrect. Why? Because of this. Magnesium is present in chlorophyll. So you must remember this. The other statements are correct. We have been asked to identify only the incorrect one. So C is the incorrect statement. So I'll say why it's incorrect, because in place of calcium, magnesium should have been there. Right? Let's move to the next question. Alright, nickel. Nickel is combining with X minus to form this complex. Alright. The number of unpaired electrons and geometry of this complex are. Alright. Now see, if I assume X to be Cl4 minus, then this is the complex. Because it has to be uninegative. Uninegative means charge of -1, right? So NiCl4 2 minus. Also, we have been told that the complex is paramagnetic. That means unpaired electrons must be present. Chlorine has an oxidation state of -1 here, which means nickel will have an oxidation state of +2 here. I have calculated the oxidation state of nickel mentally, which means let it be X, and then X plus -1 into 4 is -2, and so on. Okay. So we know that Cl minus is a weak field ligand, so no pairing will take place. Now the electronic configuration, only talking about the valence shell of Ni2 plus ion, will be this. Only for the valence shell. Okay, I've written electronic configuration of Ni2 plus only for the valence shell. So I've ignored that part, 1s2, 2s2 and all those things. I'm writing only for the last part, last shell. So it's the third shell, because I have to remove 2 electrons from 4s, and hence I get 3d8. 3d8, okay. 3d8. So 3d8 means I have to write here I have to show the boxes here. Right. 3d8. Then I have 4s, and then I have 4p. Let's use VBT, valence bond theory. Now, going by VBT, I need 4 empty boxes because there are 4 monodentate ligands, right? Cl minus is monodentate. Now, remember one important thing. This condition has to be checked. The complex is paramagnetic. Clearly, this is paramagnetic because we have 2 unpaired electrons. So, yes, it is paramagnetic, which means these 4 boxes are empty. So, these 4 orbitals are going to be used for formation of bonds. Hybridization will be sp3 because there is 1 s orbital and there are 3 p orbitals. So, sp3 is the hybridization, which means tetrahedral will be the geometry. So D is the correct answer. We know that whenever hybridization of central metal is sp3, the geometry of the complex is tetrahedral, right? And there are two unpaired electrons, so 2. So this is the correct answer. Cl minus is a weak filled ligand, so we haven't done pairing, and after there is no pairing, we can conclude that there are two unpaired electrons. Had pairing happened, then there wouldn't have been any unpaired electron because this electron would have shifted here. But now we have two unpaired electrons, and hence D is the correct answer. Paramagnetic behavior has to be shown, which means unpaired electrons need to be present. So sp3. These are the 4 orbitals which are going to take part in hybridization, and then the Cl minus will give its electron pair to those sp3 hybrid orbitals. Next one. The FeC bond possesses. Remember one thing, whenever we have metal carbonyls, so this is a metal carbonyl. Whenever we have a metal carbonyl, then the metal carbon bond is not a pure single bond. The metal carbon bond is not a pure single bond. It has both sigma and pi character because of synergic bonding, synergic effect, right? So back donation happens, and always remember that the bond between metal and carbon is never pure. It has always sigma and pi characteristics. So D is the correct answer. So synergic bonding. Metal carbonyl, very very important concept, right? So the bond between metal and carbon is possessing both sigma and pi bond characteristics. Going ahead, how many EDTA, okay, now ethylene diamond tetracetic acid molecules are required to make an octahedral complex with Ca2 plus ion? Okay, this you have to keep in mind that only one EDTA takes part in forming coordinate bonds, right, with calcium ion, calcium or magnesium. So only one EDTA molecule, ethylene diamine tetracetic acid, is taking part in the formation of coordinate bonds to form an octahedral complex with Ca2 plus or Mg2 plus ion. So keep this in mind. So answer is 1. Next one. The spin-only magnetic moment. Spin-only magnetic moment is again that same thing, square root of this n into n plus 2 Bohr magneton. Bm is the unit. Ni2 plus an aqueous solution would be aqueous solution. Alright. Aqueous solution. Aqueous solution means water is a ligand and water is a weak fill ligand. Ni2 plus. So this is similar to this concept, right? Similar concept. H2 is a weak fill ligand. So no pairing, and again we'll have the same thing. That is, we'll have two unpaired electrons, and the spin-only magnetic moment will be root of 2 into 2 plus 2. So this will be the correct answer. Right? Yes. All right. Hence the correct option is C. So it is exactly the Same. I mean, it is, I mean, this is the electronic configuration. Pairing will not happen, right? Because water is a weak field ligand. Halogen, water, all these are weak field ligands. Okay, next one. Which of the following is a tridentate ligand? Tridentate. This is bidentate. All of us remember, we know. This is also bidentate, right? This is monodentate, which means this will be a tridentate ligand. This is tridentate. Tridentate, diene. The charge is 0. It's neutral. So what is the structure of diene? You must remember the structure of diene. So this is diene. We see that there are 3 lone pairs. So these are the 3 nitrogen atoms which act as donor atoms. Hence we are saying that denticity is 3. So this is called diethylene triamine. So this is diethylene triamine, diene. Okay, next question. What is oxalate? This is oxalate. This is called oxalate. What is glycinate? These are the 2 donor atoms, nitrogen and oxygen. Hence, it's a bidentate ligand. Now remember, bidentate is also called didentate. Di can be used instead of writing bi. So bidentate and didentate mean the same. Next question. Okay. Both CO3 plus and PT4 plus have a coordination number of 6. Okay. Which of the following pairs will show approximately the same electrical conductance for their 0.001 molar aqueous solutions? Now, electrical conductance will depend on the number of ions produced on dissociation. So, we have to focus on the cation and the anion. Already, we have been told that the coordination number is 6. Okay, Cl minus is monodentate ligand because it's a halide. Ammonia is also monodentate ligand. So, all these things we are aware of. Alright, now let's see. If I talk about option C, what happens is this, that is Cl3.6NH3, can be written in this way, CO, right, CO, NH3 6, right? And this can be written as So the coordination number is 6 for cobalt here. Here also if you see, the coordination number is 6 for platinum because 5 plus 1 is 6. Now how many Cl minus ions are left behind? So already 1 has been used here. PtCl4, that means 3 more. Right? So here the oxidation state of cobalt is plus 3 and here the oxidation state of platinum is plus 4. If you compare these two, clearly when this splits, right, I'll have cation, that is this portion, the coordination sphere, CuNH3 6 times 3 plus 3 Cl minus, right? So cation plus 3 Cl minus. Similarly here, cation plus 3 Cl minus, hence option C is correct. The same number of ions is produced on dissociation. How many ions are produced on dissociation? If I assume complete dissociation of each, then the number of ions will be 4. How 4? 3 Cl minus plus 1, the coordination sphere, which is the cation. So on dissociation, the same number of ions is produced by each, hence the correct answer is C, because the number of ions is same for both. Next one. Square planar. That means the hybridization will be DsP2. Square planar, that means the hybridization will be DsP2. All of us remember that PtCl42 minus is square planar. PtCl42 minus is square planar. You can find out the geometries of the others by using valence bond theory, and then this will be the only one left. So in that way you can say that yes, PtCl42 minus is the answer, because in these, if you see, none of the central metal atoms will have DsP2 as the coordination, as the hybridization. So this is the correct answer. DsP2. Oxidation state of Pt is plus 2 here. Oxidation state of cobalt is plus 2. Oxidation state of Fe is plus 2. Oxidation state of Ni is plus 2. Next question. Very, very important question. NiCO 4 times. Again, this is what? It's a metal carbonyl. This is called nickel tetracarbonyl. And the proper IUPAC name is tetracarbonyl nickel. And then 0 is the oxidation state of nickel here. You must remember that D is the correct answer. sp3 is the hybridization of nickel here. It's a tetrahedral complex. Electronic configuration is 4s2 3d8. Oxidation state is 0, which means I don't have to remove any electron from 4s, right? Now, if you start drawing the boxes and if you follow the VBT, that is valence bond theory, okay. Now, CO is a strong field ligand. So this comes here, right? And these two come here. As a result, 4s becomes empty. So if I show the exact pairing, then what will happen? So let me show the exact pairing. hence sp3. These are the 4 empty orbitals which will be used for hybridization. So D is the correct answer. So CO is a strong field ligand and hence pairing took place. So this is 3D8, then this is 4S0, 4P0, and then these 4 are empty. Okay. It's diamagnetic because there is no unpaired electron. Next question. Wilkinson's catalyst. Now again this is important, you have to remember this, right? This is called Wilkinson's catalyst. RH is rhodium. This is Wilkinson's catalyst. It is used for hydrogenation of alkenes in organic, right? You have to remember that the +1 is the oxidation state of rhodium here. What is this? This is triphenylphosphine. Right, triphenylphosphine. Right. So this is Wilkinson's catalyst and A is the correct answer. So you must remember this. 4 is the coordination number, right? DSP2 is the hybridization. It is a square planar complex. Okay, next question. Not an organometallic compound. So we have discussed in the beginning itself, not an organometallic compound. That means it should not contain any bond between carbon and metal. This is organometallic because we have zinc and carbon which are connected via bond. Again, this is organometallic, right? Then, so which one is the correct answer? So, which one is not an organometallic compound? So this is not an organometallic compound. Because again, if you see, oxygen is bonded to boron and oxygen is bonded to carbon. So there is no bond between carbon and metal. Right? Next one. Which of the following facts about the complex this is wrong? Alright, which is wrong? Outer orbital complex, inner orbital. Okay, let's prove this. Now we have to use VBT for this. So the oxidation state of chromium comes out to be +3 here. NH3 is neutral. Cl is having a charge of -1. NH3 is a strong field ligand whenever we have +3 as the oxidation state of a 3D metal, of a 3D series. So pairing will happen, right? Let's see now. Now chromium. So 4s13d5. This is for the neutral chromium atom. +3 indicates I have to remove 3 electrons. So 1 from here and 2 from here. So 3d3. 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 So this is This is 4s. All right. Because NH3 is a strong field ligand, right? Pairing will happen, which means this comes here and this comes here, right? Okay. First of all, you have to understand that now if we use the, so again there are 5 orbitals in D, right? So let's see. So 1, 2, 3, 4, 5. This is 3D, 3D3. Then we have 4s, and then we have 4p. All right. Because this is a strong field ligand, pairing will happen, and if pairing happens, then we'll have this, right? This is what will happen. Okay. And if pairing does not happen, then this will be the arrangement. Now see, very, very important. From here we arrived at 3D3 because we had to remove 3 electrons. So 1 from this vent and 2 from this vent. So 5 minus 2, 3, 3D3. After drawing the configuration, clearly we see that even if we don't make these electrons undergo pairing, even if pairing does not take place, still we will have 2 empty d orbitals, which means here there is no need of pairing despite the fact that NH3 is a strong field ligand. So it is always not mandatory that pairing will happen if there is a strong field ligand every time, which means here these are the 2 empty orbitals. So 2 d orbitals, 1 s orbital is there, and there are 3 p orbitals. So we need 6, right? So 1, 2, 3, 4, 5, 6. 6 empty d orbitals, 6 empty orbitals which will undergo hybridization. So 3d, 4s and 4p will take part in hybridization, which means the hybridization will be d2sp3. d2sp3. d2 indicates these 2 orbitals of 3d have been used. 4s, so 1s of 4s, and then there are 3p orbitals of 4p. d2sp3 is the correct hybridization of this complex. It's a paramagnetic complex because we have 3 unpaired electrons. Yes, so D is correct. Now D2sp3 indicates it is an inner orbital complex. Inner orbital complex. Option A says the complex is an outer orbital complex. So this is incorrect. They have asked us to identify the incorrect statement, right? Wrong means incorrect. Definitely this will give a white precipitate of AgCl because AgNO3 is added and then Cl minus is outside the square brackets, which means AgCl will be formed as a precipitate. AgCl will be formed as a precipitate because Cl minus is the ionization sphere, right? So B, C, D are correct statements. A is incorrect. Next one. Which is the correct order of their increasing field strengths? Now this is directly from the spectrochemical series. You have to memorize the spectrochemical series given in NCERT, right? And the correct option is, this is the correct option, right? What is this? Ethylene diamine. So B is the correct answer. Let's move to the next question. Which of the following complex ions has geometrical isomers? Okay, this is the correct option. Now see, C is of the form M A twice B2. Right? This complex has 2 NH3 as ligand. So this B indicates a monodentate ligand, that is NH3 here. And this indicates a bidentate ligand, and that too where both the donor atoms are same, just like En. What is En? This is En. So if you look at En, both the donor atoms are same. Both are nitrogen atoms, right? Which means En belongs to this category, A category, and NH3 is just normal monodentate ligand B2. So this has geometrical isomers. Cis and trans forms are possible for this, right? If you have the two B on opposite sides, then it is trans. So cis and trans isomers are possible, which means yes, geometrical isomer is possible. All other options have no geometrical isomers. Always remember, if you get a question on isomerism, convert it to this form first and then start checking. Next question. Which among the following will be named as dibromido? Bis. Bis means 2 times ethylene, diamine, chromium, 3 bromide. Let's see. Now dibromido means this. Bis ethylene diamine, that means 2 times we have En. Chromium, this is chromium, and then we have bromide, so this will be bromide. Let's check the oxidation states now. 3 means here plus 3, this is minus 1, it's a halogen, this is a neutral ligand. En is also neutral, so 0, which means plus 3 minus 2 plus 0, this will be equal to plus 1. So plus 1 minus 1, yes, so this is the correct complex. So let's check the option. So CrN twice, Br twice, or Br2, then Br. So option C is the correct answer. Okay, next one. Question. This question is again related to absorption of wavelengths. Okay, red, green, yellow, and then blue. Now we have learned again that energy absorbed will be inversely proportional to the wavelength absorbed. And this is high if the strength of ligand is high. Which means if this is maximum, then this is minimum. When is this maximum? For red, obviously we know within the visible region, red has the maximum wavelength. So red, that means when the red wavelength, red light is absorbed, so wavelength is red, that means the energy will be minimum. If energy is minimum, that means the strength of the field is not that much, right? Okay. Okay, so in which case is red absorbed? It has been mentioned that when L1 is the ligand, then red is absorbed. Okay, so L1 is the ligand corresponding to which wavelength of red light is absorbed. If wavelength of red light is absorbed, minimum energy is absorbed. Minimum energy means this has the weakest. So this is weak. Weak. Or rather weakest, I should write. Weakest. Which means either option B is correct or option D is correct. Now, blue. Out of red, green, yellow and blue, blue has the shortest wavelength. If blue has the shortest wavelength, that means the ligand corresponding to blue will be the strongest. So blue means which one? 4th, right? So L4 is the strongest. So L4 is strongest and L1 is weakest. So D is the correct option. Next question. Which of the following statements is or are correct? Yes, very, very true. You have to remember this always. Ag always forms linear complexes, right? And the coordination number of Ag is 2. NiCO4 times has been discussed today. MnO4 manasis, paramagnetic ion, yes, tetrahedral geometry. So this is also correct. Yes, this is also correct. This can be verified using VBT, which means D is the correct answer. So all are correct. Right? All are correct. So I hope everything has been clear. So please don't ignore this chapter. It's a very important chapter. All the best for your NEET. Do well, stay calm, give your best. Believe in yourself. Thank you.